Good day, everyone. I'd like to welcome you to the Municipal Sustainability Forum. I'm Sierra Dahl, and I'll be your host. Thanks for joining us. We're going to hold questions until the end of the presentation. Our presenter today is Greg Thompson. Greg is Programs Director for the Clean Coalition. Having delivered successful software and data platforms for over 15 years, Greg is now applying his experience and drive for innovation to the advanced energy industry. At both startups and large corporations, Greg has simplified complex market and technical issues into differentiated strategies and solutions. Greg leads the Clean Coalition's Community Microgrid initiative, demonstrating to key industry stakeholders that communities can support much higher levels of local, cost-effective renewable energy. He has authored a seminal paper defining DER optimization methodologies and was a leading contributor to the California Public Utility Commission's draft for ruling on distribution resources planning requirements for California utilities. In his recent past, Greg delivered an industry-wide application platform plan and financial opportunity while Vice President of Advanced Product Development at Comcast Cable, the largest cable operator in the United States, representing around $1 billion in incremental revenue. Prior to that, Greg developed and led product management and business development for a 100-person startup at the conversions of the internet and video, helping achieve a successful acquisition by a Fortune 100 corporation and deployment to over 60 million consumer devices. Now, I'd like to welcome Greg.
Great, thank you, Sierra. Appreciate that introduction. And as Sierra mentioned, we're going to talk about community microgrids today. And I'll start with the agenda. So we'll do an overview of community microgrids. What are they and why they're an opportunity for scale and cost effectiveness for local renewable energy systems. We'll talk about the methodology for planning a community microgrid and then deploying them, and we'll give some examples of that methodology. And then I'll talk through a couple of existing projects that we're working on as case studies for proving the model, for proving that these are really the opportunity for modernizing the grid and achieving cost effectiveness with local energy systems. So I'll start with our view of the modern grid. So we see the grid being modernized with a lot of what is called, of course, distributed energy resources, and this includes solar, it includes wind where it's appropriate, biopower, energy storage, all kinds of distributed generation with electric vehicles, of course, tapping into the grid. And then sophisticated monitoring, communications, and control systems that can actually optimize all of these resources, orchestrate them, make them work with the grid. And our approach is that we can achieve local renewables at least 25% minimum in terms of the annual energy that those local renewables provide to customers and to the grid. So we see that 25% minimum as the baseline or the target for what we can achieve with community microgrids, in particular in this picture here that we're looking at. So what are the benefits here of a community microgrid? Our community microgrid initiative actually proves that they offer a more scalable, more cost-effective, and modern solution for our grid. So those benefits include scale and sustainability. So again, where local renewables can achieve 25% to 50% of the total annual energy that is consumed in an area. And that's a good number to look at and target, because if you think about where solar is today, including not only distributed solar, but also centralized solar, it's at less than 2% of the energy that we consume today here in the United States. So this is really taking a number like 2% and getting it up to 25 to 50% through a approach that makes that really work. And one of the things that really makes it work is this approach is cost effective. So this is achieving lower long-term costs for ratepayers by a couple of things, key things here. One is by technology, using technology versus commodities. So there's quite a bit of an advantage over the long term in using technologies because those technologies the cost of those technologies come down over time. As you scale up those technologies, right, the cost comes down. So think of televisions, VCRs, obviously computers and cell phones. The more you get out there, the more the cost comes down. That's equivalent to using technology for energy, such as solar or wind or energy storage, where the more you deploy that, the more the cost comes down. We've seen, obviously, very cost-competitive solutions in wind, especially at the moment, with solar obviously reaching grid parity soon. So that's one of the big benefits of scaling renewable energy, local renewable energy especially, is getting that cost advantage. The other key cost effectiveness is when you're working on local energy systems, you're actually looking at some of the things that cause the most cost in the electrical grid, such as peaks. Peaks across a bunch of multiple distribution grid areas, are why we have to spend more money on transmission or spend more money on peaker plants. And so we look at community microgrids as taking that significant cost out of the system. And of course, also when you're producing energy locally and using it locally, you're not using the transmission grid for that. So you're saving in not only the sending electricity over the transmission infrastructure, but you're saving money and not having to build new transmission infrastructure for satisfying that local energy, that local load. So that's a really important area where we can find significant cost savings simply by taking a look at the electrical grid and applying a distributed model to it rather than the centralized model that we use today. Third real huge benefit that goes with that is local investment. So whenever you're putting local energy systems in, you're actually spending substantial dollars on local and regional jobs instead of spending those same dollars remotely or offshore. And I'll actually show some examples of that as we get through here through the presentation. But there's some big numbers that you can really apply to local economies by putting in a community microgrid approach. And then finally, this is really one of the most important benefits, especially for the East Coast and states like New York and New Jersey and Connecticut, based on things like Hurricane Sandy. What we really need is a much more resilient and secure electrical system. We don't really have that today with the centralized model. So this improves grid reliability. It improves resilience, meaning if the grid goes down, you can still provide power locally, and that's a critical thing for communities and cities, as well as security. And so if there are events that bring the grid down, we have the security and resilience we need if we are generating or producing power locally and using it locally. And this is also a replicable model, and so this can extend across any area, any community area, any city area, any utility service area. So the result here is a much smarter distribution grid with more clean energy, better grid performance, and finally stronger long-term economics. So I'll get into the definition here. What is a community microgrid? So it is a new approach, and it's how we want to design and operate the electrical grid going forward, getting us to that more sustainable and cost-effective energy system that I've been talking about here. Key features are you pick a targeted and coordinated local grid area, and that can be served by one or more distribution substations. We achieve high penetrations of local renewables and other distributed energy resources, such as energy storage and demand response. So you're looking at that grid area, you're coordinating these local renewables and other DER, and you're getting the most out of them in that particular grid area, whether it's a single substation or multiple substations. Another key feature is providing ongoing renewables-driven power backup for both critical loads and prioritized loads across the grid area. I'll speak more to this later, but going back to the resilience and security needs we have for our grid, this is one of the key features that community microgrids provide. And then again, it's a solution that can be readily extended throughout a utility service territory. It's a building block, it's a Lego, and if you can achieve this in one substation area, you can achieve it across many and replicate that across utilities as well. This is really a systems approach to planning and operating the distribution grid, and so why does this matter? It's really analogous to one of the biggest innovators in our history here, which is Henry Ford, and how his assembly line changed the economics and scale of the automobile industry and of manufacturing in general. And when Henry Ford created the assembly line approach, he wasn't inventing a new internal combustion engine or other car components. They all existed before the assembly line. Just as solar panels and inverters and energy storage exist today. What we need is scale in those components. So rather than producing individual cars one at a time, Ford shifted the thinking to really what's the higher level system that we can use here to really get to economies of scale and get to price points where lots of people can participate in owning and enjoying cars. So similarly, today in our electrical system, we have the same opportunity. So we can bring all the elements together of energy systems that feature local renewables and feature other distributed energy resources. We can bring all those together into an assembly line approach. And that assembly line approach will get us to be able to attach renewable energy in bulk amounts. And that will get us to the resulting benefits that we need, which is scale and innovation and cost effectiveness. So to give you a couple of examples of that, so we really today have a one rooftop at a time approach to attaching local renewable energy systems. It's very slow, it's very costly. As we know, our soft costs here in this country are way too much and contribute to the slow deployment of local renewables. It's also an approach that's disruptive to the grid. So as the utilities are operating the grid and people are knocking on the door saying, hey, I want to attach this, solar array or this project, they have to react to that rather than what should be happening is they're planning for these systems to be attached to the grid. So we think of this as local capacity targets, essentially planning the grid for a specific amount or range of local renewable energy systems. And that's how we can achieve scale and lower cost and also stability of the grid. And this is a plug-and-play method. And here in California, the state talks about needing a plug-and-play method for distributed energy resources. The same applies to many other states in the country like New York and Connecticut and Massachusetts and New Jersey. Everyone's trying to figure out, okay, how do we take the existing distribution grid and have things really plug and play? And so this local capacity target model, the community microgrid approach, is the way to do that. And these examples here are really just examples, but you could have targets, a lower capacity target of, say, 15 megawatts with no grid upgrades needed using advanced inverters. You might have a medium capacity target that get you to 30% of total energy, maybe 30 megawatts, and you're adding some cost-effective storage and demand response. Or you might want to go higher, so a higher capacity target of 45 megawatts, where you can actually island or provide backup power to the critical services and get more peak reduction with more storage, etc. And again, these are just examples, but the point is we want to get to these numbers in the planning process and then make sure the grid is capable of supporting that, and then we can actually connect everything in bulk amounts. So what's the difference here between community microgrids and traditional microgrids? Because the word microgrid, of course, is used quite a bit across the industry, and we want to be very clear what a community microgrid is versus traditional microgrid. So as most people know, traditional microgrids really focus on single customers, so single sites, single buildings or single compounds, etc. And so all the benefits go to that single site for the most part. A community microgrid by contrast, serves thousands of customers. So all of the customers that are part of a community microgrid area, whether that's one substation or multiple substations, benefit from everything we've talked about with community microgrids. So you might have all sorts of shared energy across that area. You have shared benefits in terms of critical and priority loads being provided energy during outages, and you have all the cost benefits that apply across the area as well. So that's the overview of community microgrids, what they are, and the opportunity to use them to achieve the scale and cost effectiveness that we've been talking about. So I'm going to move on now to a little more detail. We'll talk about the methodology for how to plan for a community microgrid with some examples of that methodology. Okay, this is a busy slide, and I'm going to go through it pretty quickly because we have examples coming to show, what we're talking about here. But essentially, we organized this into 6 steps. So a community microgrid in 6 steps. And as you can imagine, the first step is, what are the goals? So what are the desired performance metrics? What's the amount of local renewable energy we want? What's the grid reliability and power backup and peak reduction goals we have? And setting those goals is very important because there's a lot of different ways you can achieve the goals, and so you want to know what you're going after, and then you can adjust things to get to the finish line as you go forward. Second step is understanding what's there already. So this is a baseline grid analysis, an inventory of the existing grid assets, including load profiles, the grid operations, existing generation, and this also includes understanding which critical and prioritized loads we really want to provide power to in outage situations. And then step 3 is, what's the renewable energy that's really viable in that area? So renewable siting survey that gives you that number and gives you the locations, informs the other requirements such as energy storage, capacity, and control system functionality. So you're really looking at what's the asset here in the community in terms of energy generation. And that's obviously, it's not random. It's very targeted in terms of where you want to use those assets. If you put all those things together, basically the next step, number 4, is what we call DER optimization. And this is designing optimal portfolios of distributed energy resources, including managing loads based on those resources. This incorporates the baseline grid analysis, combining that with the renewables in the area to create what we call this the DER portfolios that really optimize all these assets. And part of that is sort of in parallel, although we call it step 5, is doing the economic analysis. So as you're designing these DER portfolios, you're looking at the cost benefits and net value. You're looking at cost reductions in transmission and distribution grid, infrastructure, and other ratepayer benefits, peak reduction. You're looking at local job creation. So you're kind of putting together really how does this benefit ratepayers, how does this benefit the utility and the community as part of designing this whole system. And once you have all those pieces together, you can get to a deployment plan. So this would be the final system design, the financial model, the operational plan, all the requirements and vendor analysis included here so that you're matching, technologies to the design. So I'm going to go through now and talk about some examples here so you can get a little bit more out of what we mean by these 6 steps. Goals, and I'll go through this pretty quickly. This is pretty self-explanatory. So targeting at least 25% of the total electric energy consumed within the target grid area. Saving ratepayers money would be obviously a goal. So deferring investments in transmission and distribution infrastructure, and that's achieved through local balancing. We call that local balancing, which is load shifting and peak shaving, essentially. Improving the grid performance would be another goal. So getting to the quality, reliability, the resilience, and the security that you want, leveraging the local renewable energy and energy storage to provide ongoing backup power. to the specific critical and prioritized loads that you've targeted. And the other goal really is a general goal, but it's looking at how to deliver a cost-effective and accelerated path to modernizing grid operations and achieving this distributed energy resources future that we're all working towards. Now, you may have more specific goals if you're actually planning for a community microgrid in a specific area, but this is just a high-level example. So step 2, the baseline grid analysis. So this is determining what's there. What's the ability of the grid to accommodate new distributed energy resources today. So an inventory of the existing grid assets, including the load profiles, the voltage regulation equipment. So there's, obviously load tap changers and voltage regulation happening today in the distribution grid. It turns out that you can leverage that to support local renewables to a certain degree without requiring a lot of investment. So you're really getting to, what are the feeder and transformer capacities that exist today, allowing the connection of renewables in bulk amounts. What's the existing generation? And an example of a grid analysis that's happened that really has a big impact is here in California, the distribution resources plans that the utilities were required to provide. There's a ruling from the California Public Utilities Commission, which some of the methodologies I'm talking about today, we actually contributed to that final ruling. And essentially it's saying to the utilities, okay, we know you have a grid out there. This has never been done before, but tell us what the real capacity is of the existing grid for supporting distributed energy resources. And that's already gotten us quite a bit further in terms of what we understand is possible than what we had before. So we can support a lot more local renewables than we thought because of that simple analysis of the existing grid. Well, I shouldn't say simple. It's not simple, but it's possible with today's tools. And so it's been done, and the utilities have delivered those plans, and that's gotten us a big step forward here in California. Step 3, the Renewable Energy Siting Survey is looking at, taking a comprehensive assessment, looking at the local renewable energy potential in the grid area, and that's specific, of course, to local resources and local site characteristics. An example of this is a solar siting survey that we completed for Southern California Edison recently as part of their preferred resources pilot area. So it's approximately 120 square miles in Orange County, California. We found a potential resource of over 160 megawatts for new solar, and that was on large rooftops, parking lots, and parking garages, so 500 kilowatt and above. So it's essentially a look at, for the most part, the commercial and industrial opportunities in the area. We identified all these locations, and you'll see in the map there, the sun icons, of course, represent those locations that we analyzed with the amount of kilowatts per location. And if you click on any one of these sun icons, you get a pop-up here. You'll see this info panel here, which shows you exactly the amount analyzed per location, the address, the square foot area of the viable PV part of the rooftop or parking lot, the type of structure, whether it's a flat roof or angled roof or parking lot, or whether it's actually a group of potential areas in, say, a shopping mall, for example, or an office park, and then distance to the closest feeders, which helps with planning interconnection. We also actually went through and rated the density potential of the rooftop or parking lot. So any rooftop, for example, that you can get a lot of a high density of solar panels on, we call that a high density rooftop. Obviously there's medium and low. Low, of course, would have lots of things in the way, but you can still get a decent amount on the roof. So we were able to actually categorize the potential for each of these opportunities. So once you have the goals, you've got the existing grid assets really understood, and you have the solar potential or renewable energy potential figured out, you then move to this step 4, which is really the core of getting the most out of the existing distribution grid and the local energy assets. This is what we call the DER, Distributed Energy Resources Optimization Methodology. There's a few inputs on the left, so the existing grid, we talked about that already. The DER solutions, so that's the Renewable Energy Survey, solar installation, weather forecasting, etc. And then we take these inputs and we do this 4-step methodology, which is modeling the baseline power flow, making sure you have that correct and accurate with all the data sets. You've got to have that foundation, otherwise everything you do on top of that is going to be incorrect. And then we take that next step, which is looking at the lower capacity. If you remember those plugs in the previous slide, this would be sort of what is the capacity of this existing distribution grid that doesn't require upgrades, manages voltage with the existing equipment, and uses advanced inverters when needed. And you're really optimizing the locations, the sizes, the types, the costs, and the deferrals of all of these DER assets when you're looking at this. And this, again, is very analogous to what the California utilities have done with their distribution resources planning, which is what is the capacity of the existing distribution grid to support local renewables and other distributed energy resources using optimal locations. So that's the next step, and you want to do that step second because that's how you get the most DERs with the least amount of cost to the grid. And that's, again, your foundation. That's like if the baseline power flow is the basement, the lower capacity step is the first floor, and you can't build other floors on top until you've got a good foundation and a good first floor. So that's how you get through this really in the most cost-effective way. And then you can add more capacity. We call that the median capacity step in terms of adding cost-effective storage, adding in demand response that's targeted to those local resources. May require some moderate grid upgrades, but again, you're optimizing everything in terms of locations, sizes, types of DER, cost, etc. And then finally, a higher capacity target would be adding more storage, adding more local generation, doing things to continue to reduce peaks and variability, and then adding in more resources to make sure your critical loads and your priority loads can be supported in the case of outages. And the outputs of doing this methodology are really, like we've said, a scalable and cost-effective and operationally viable community microgrid plan or DER optimization plan. And the results are validated with the utility and the technology vendors, and you're maintaining and improving, in fact, grid reliability and power quality, and adding in resilience and security. And a couple of quick slides on DER optimization just to provide some examples and to make some points. So I like this picture a lot because it's really what it's all about. Local is fundamental to how we should be operating the grid. That's where the loads are. We have an opportunity to add a lot of generation in a cost-effective way. And it's sort of like, the old reading is fundamental program for helping kids to read. Well, local is fundamental here, and it's a combination of things, of local variables that you put together to create optimal DER portfolios. I'll quickly talk through these, but it's optimal feeder locations in combination with all these other characteristics. We talked about feeder capacities and picking the right locations. I'll speak to that in a little bit more in a second. Using connected feeders at a substation is a big deal. Having those connected feeders means you can have overgeneration on a feeder, and you can share that overgeneration of energy with other feeders that are connected. For example, we had some overgeneration in one project that we worked on with PG&E on a feeder, and that was a feeder that had more commercial and industrial customers, and we had a lot of solar on that feeder in our model, and that extra energy just flowed onto the adjacent feeder where we had a lot of residential folks. And so really it's a self-balancing mechanism, and it's really a critical feature of operating the distribution grid going forward. The local load shapes and forecasts, and I'm right here now, are also critical. So customers and different customer types have different load shapes. You can find some common themes by looking at, for example, the load shapes of residential customers versus the load shapes of commercial and industrial customers, and that helps you optimize those DERs. And again, that actually helps, it helps you understand how things like connected feeders can be an asset, help you balance things locally. And then the next thing is avoiding local grid upgrades. So this is using local generation and energy storage to slow down the need to spend a lot of money on distribution grid components like transformers. And this also extends, of course, to system-wide avoided costs, such as transmission costs, which I mentioned earlier. And then finally, the last local element to integrate into a DER portfolio plan, into a community microgrid plan, is the local market value. So the local market value of supporting critical loads and supporting prioritized loads through a substation-wide system or a community microgrid, it has significant value. And so it's more reliable. It's also more predictable in terms of costs for those customers, and it's cleaner. So there's a lot of value here for the ratepayers and the residents of a community microgrid. And that value needs to be taken into account. So those are all the local aspects that together give you this optimized community microgrid system. Another optimization is using advanced inverters, and this just shows how you can have overvoltage with local generation, but that overvoltage can be really handled nicely because we've got advanced inverters who can stabilize that voltage, can provide reactive power, for example, to bring that voltage back down. And this is one of the features that we have with new technologies, advanced inverters, that just make this operationally really viable. Another optimization, and I've talked about this a bit, I'm going to spend a second here, but you're looking at customers, you're looking at the feeders, the existing grid, you're looking at loads, and one of the things that's very clear is that the commercial and industrial segment really is a great match for solar, especially. I mean, they're the largest electricity users typically, which means they're also often the largest emitters of greenhouse gas emissions in cities and communities, and so they're really an opportunity to take solar systems and storage and local energy systems and say, okay, how do we apply this to this customer segment and really take advantage of this low-hanging fruit? They have the most generation opportunity. They've got the largest rooftop spaces, which generate more energy, and those larger systems, bring the lower costs for installation, and so they reduce overall costs. They're on the best grid locations because essentially the large loads they have are served by more robust feeder segments, and those more robust feeders can handle more local generation, and they have matching load profiles. They're using a lot of daytime load typically, right? So this is a generalization, but it's pretty common. So those large daytime loads match solar generation, and they're financially motivated. So they have large bills, including demand charges, and plus leasing opportunities for their rooftops. So if you look at this customer segment and you say, why aren't we doing more with these customers today? They're a perfect match to help solve grid issues and bring scalability to local renewables. Moving on to step 5, economic analysis, economic and benefits analysis. So this is an example. I'm just going right to an example. Essentially, every community microgrid will bring energy benefits, economic benefits, and environmental benefits. And in our work with PG&E on the Hunters Point project, we analyzed the benefits of bringing 50 megawatts of new solar in. And over 20 years, basically these benefits include the following. So cost parity with natural gas, that's a levelized cost of energy cost analysis. $260 million dollars spent locally on local energy versus remotely. 80 million in avoided transmission costs and 30 million in avoided power interruptions. So right there you see the benefits of a local energy system. There are significant other economic benefits other than the amount spent locally on energy. And that's 200 million in regional impacts and regional investment, 100 million in added local wages, 1,700 job years, both in near-term and ongoing employment, and then 10 million in site leasing income. And finally, on the environmental side, it's reducing annual GHG emissions by 78 million pounds, saving water annually by 15 million gallons, and then preserving lots of land because you're using the built environment essentially for generating energy rather than creating new transmission and other things that take up acres of land. So there are significant benefits to, again, looking at a distributed model for our electrical system and building community microgrids to achieve all those economic, energy, and environmental benefits. And then finally, step 6, once you've gone through all that, you've got really a final system design, financial model, and operational plan. You've got vendor analysis through RFIs and RFPs that are appropriate to the design criteria, and a financial model for deploying it, and then all the operational requirements. All right, so that was the details on the planning for community microgrids, the methodology, how to get to DER optimization that's really cost effective and operationally stable and get you to the scale you need. So now I'm going to talk about a couple of existing projects, and these are good case studies. These are projects that we're working on actively. First one I mentioned before, of course, we talked about the benefits of the Hunters Point Community Microgrid project of bringing 50 megawatts of new solar there. So this is a project in collaboration with PG&E. It's pretty much an innovative approach. It's the community microgrid model, essentially. And it really is what we used to develop the DER optimization methodology that was incorporated into the California Public Utility Commission's distribution resources planning requirements for the utilities here. It's really a showcase, showing the value of a community microgrid. And we achieved the sort of DER optimization using existing tools. And so there are multiple tools out there that you can use to do this. We used SIM's distribution grid modeling tool, and it can be replicated fairly easily. We also were the benefit of lots of collaboration with Integral Analytics, which is an organization that does a lot with smart meter data and analyzing costs. So we were able to work with both companies and achieve this, and so obviously any utility can do this. And the Hunters Point, this is a substation area community microgrid, and it serves about 20,000 customers in the Bayview, Hunters Point area of San Francisco. So about 90% of those customers are residential, 10% commercial and industrial. But the interesting thing about it is it's a kind of a common proportion of residential and commercial and industrial. And what we learned, of course, is that the loads from the commercial and industrial sector in that area really were significant. And so we could achieve a lot by focusing on that area, just as I mentioned earlier with the nice match with solar. So here is the whole area, and you can see the Bayview area to the left, Hunters Point area to the right. That whole area to the right of the red pins, the Hunters Point area, is being redeveloped over a number of years. And so our modeling focus was on the left of the red pins. You can see the residential areas and then the two commercial and industrial pockets, essentially. So we've been working on this project and used it, as I mentioned, as a showcase for the DER optimization methodology. Essentially what we proved is that we were able to get to 30 megawatts. Now the other 20 megawatts that get us to the 50 are in that area to the right of the red pins in the redevelopment area. So we focused on the 30 megawatts for our modeling exercise. And so we were able to get those 30 megawatts in to optimal locations. And that got us to 25% of the total annual energy. And we had no adverse impacts to the grid doing that because we chose optimal locations and we looked at loads and we looked at feeder capacities. We looked at the generation potential and we matched all that. It's a kind of a puzzle. You put it together in the right way and you can get a lot out of it. So we got 20 megawatts on select commercial and industrial sites, matching the low resistance areas of the feeders with higher daytime loads. We got 10 megawatts on select multiple dwelling unit sites, so apartment buildings essentially, which typically are also on more robust feeder locations. We had no out-of-range voltages, so we achieved voltage regulation with the existing load tap changers, so we didn't even bring in advanced inverters yet into the model. And we had no backfeeding to transmission. So we had some cross-feeding between feeders, as I mentioned earlier, but nothing backfeeding to transmission. So this was kind of an initial optimization step, and you can of course imagine adding in advanced inverters, adding in some targeted demand response, adding in energy storage. We're going to actually get this to quite a bit more than 25%. Moving over to New York. So New York has a very ambitious energy plan to create a comprehensive roadmap. It's called New York Rev, for those who know, to build a clean, resilient, and affordable energy system, rely on greater investment in distributed energy resources, and facilitate development of innovative community microgrids. Their plan is to, again, go back to this plug-and-play idea and figure out how to make the grid plug-and-play for these valuable distributed energy resources and get to a 40% reduction in greenhouse gas emissions by 2030 from 1990 levels, 50% generation from renewable energy sources, and then 23% decrease in energy consumption in buildings from 2012 levels. So our project in New York, we call the Long Island Community Microgrid Project, and this fits right within the state of New York's goals, their New York Rev plan. And this is a community microgrid that was awarded a New York Prize grant by NYSERDA, and it's a collaboration with PSE&G Long Island, the utility there, and the Long Island Power Authority, which owns the grid there, and of course NYSERDA. And this is a substation in East Hampton, New York, on Long Island that serves thousands of customers. And for this project, we're combining 15 megawatts of local solar, that's solar that's being procured through a feed-in tariff, with a 5 megawatt, 25 megawatt hour battery system, as well as some distributed energy storage at critical load sites, and then targeted load management based on this DER portfolio. This system will reach almost 50% of the total annual energy from local renewables. And it will minimize, or in some cases eliminate, the use of existing fossil fuel generators, which are basically diesel generators. There's a lot of diesel generation at the substation they use to deal with summer peaks in the area. And there's also diesel backup generators that we will be minimizing or replacing with local renewables and energy storage. This system will provide ongoing power backup to multiple critical facilities as well as other priority loads across the area. So that system will serve not just the critical locations, but will provide energy to other priority loads as well, because it is a community system. And it will set the stage to preempt hundreds of millions of dollars in transmission and fossil generation investments. And I wanted to finish up by showing this design template. This is really the design of the Long Island Community Microgrid project, and it really is a design template for any community microgrid. I'll just point out a few things here. I know it looks busy, but it's actually pretty straightforward. So you can see we have a bunch of solar arrays around the community area. The community area is fed by the substation, the East Hampton GT substation. And these are the two feeders coming off of that substation here. And so we've got 15 megawatts of solar with all these different solar arrays. We're using large energy storage at the substation, so 5 megawatts, 25 megawatt hours, to manage, to deal with these peaks that happen there in the summertime with all the summer visitors. And that's eliminating very costly transmission investments. Now you'll see that we've organized the loads into 3 tiers. So there's tier 1, which are the 3 critical facilities that we're supporting with this community microgrid. And then we have tier 2 loads. And then we have that are here, and then tier 3 loads. And so what you're looking at is a system that is able to support each critical load, critical facility, through the local on-site or nearby solar combined with the energy storage that's located here. In the case of an outage, this switch will open, of course, and this is a self-sustaining system for that critical facility. This switch may close and be able to provide even some additional solar that may be remote, not on-site, but close by. So this local microgrid works for each of the critical facilities. Now, if the transmission grid goes down, what we have is an opportunity to use all of the solar to support, and all of the energy storage to support not just these critical facilities, but also these tier 2 loads. So tier 1 being critical facilities and tier 2 being priority loads, we can support both of those with a lot of local energy because we have a community microgrid designed and deployed and running below the substation area. So anytime the transmission grid goes down, we can leverage all of those assets to support the entire community area. Anytime a feeder goes down, we can leverage the on-site assets for the critical loads to support those loads. Again, this is really a template for how to design and roll out a community microgrid in any substation area or areas or any utility service area. And this is how we achieve the benefits we've been talking about for scalability, for clean energy, and for cost effectiveness. And finally, a peek at our community microgrid future. And that is the presentation for today. So we'll stop here and we'll take questions.
Okay, thanks so much, Greg. Excellent presentation. A lot of good information here. And I see people found the chat feature on the left, so go ahead and type your questions in if you have any questions, and we'll take them as they come in. So Barry is asking, in the HP example, if the 300 megawatt of PV on relatively large scale existing commercial and multifamily buildings is built out, what would be the implication for future further installation of small-scale systems in the same area, if any?
Yeah, good question. So we achieved the 30 megawatts with the commercial and industrial, 20 megawatts on commercial and industrial, and 10 megawatts on the multifamily dwelling units, apartment buildings. And so this would be a stable grid supporting that amount of local renewable energy. So there really, wasn't an implication for further installation of small-scale systems. So in other words, you can add residential systems to that because residential is, somewhat a slow process. We didn't see that there'd be any implication, but we hadn't even gotten to adding in energy storage, for example, at the substation or distributed energy storage. And so we feel like there's quite a bit of opportunity to add a lot more renewable energy there using the techniques that are readily available and cost effective today. So yeah, more could be added, and a lot of those could be residential.
Karen Coleman has a question. What was the total installed cost, or B, cost per kilowatt hour per watt? That is the first one, was the kilowatt hour, and the second one actually delivered to the consumer in the Long Island example.
So actually, we are in the middle of our economic analysis for the Long Island project, and the person on the Clean Coalition staff who does that is Sam White, and so I don't have the number for that yet. But the cost per watt that we used for Hunters Point was $3.75, and that was it was looking at obviously the larger systems for commercial and industrial. And for apartment building rooftops, but blending in also the higher cost for residential. So I wish I had the number for you for Long Island, but I don't have that right now.
All right, and Shalom has a question. What acts as the voltage source for the East Hampton microgrid if there's an LIPA outage?
I'm not sure if I understand the question. I apologize. If there's an outage in the grid, the energy source, of course, is the local solar, and we would use advanced inverters if needed to regulate voltage with that energy source. There may be somebody more technically, knowledgeable that can answer that question. If I didn't answer it.
Sorry, Cal Broomhead is asking, has there been any proposal about ownership and financing? Good question. I was going to ask the same thing.
Yeah. So the proposal that's on the table for the Long Island project is the following: is the solar would be procured through a feed-in tariff, so the utility, PSE&G would procure that energy through a PPA, with partners installing and owning the actual solar. The large energy storage at the substation would be owned and operated by PSE&G, so by the utility. The entire system would be what we can say in front of the meter, or operated and optimized by a control system that the utility would own and operate, because we want to leverage all the solar and all the storage on a daily basis as needed, and in ways that are optimal for the grid, and in ways that get benefits in terms of services to the grid. So even the storage that's located at the critical sites, so those 3 critical sites that will have some energy storage there, that storage will be in front of the meter and part of the entire system. So one thing that isn't clear is whether that storage will be owned by an aggregator or owned by the critical site, but it will be included in the operations that the utility handles. So that's sort of where we are today with ownership and financing.
Robert Perry is asking, the 5 megawatt ES example, is that the total capacity, megawatt hours, or output, or if output, how many megawatt hours have modeled?
Yeah, it's the output, so it's 25 megawatt hours of output.
Okay. Here. Barry Cooper. Which of the projects described today are built out or have committed capital to resolve it?
Let's see. So the Hunters Point project is moving forward, but we don't have commitments yet. So still being discussed and planned. The Long Island project is, again, as mentioned, is funded by NYSERDA for going through their New York Prize process. So we're in the feasibility analysis phase right now, and that will take us through the end of the year. As I mentioned, we're going through the financial analysis, so I don't have those numbers yet. We don't have the answers on that yet. Next year, once we get through the feasibility analysis, it moves to stage 2, which is a audit grade technical and financial plan. And then that stage is what will set us up for deployment, which we hope will happen late next year. There is a commitment by the state, and there's a commitment by PSE&G and NYSERDA to solve the problems in this area. There's just an issue with peaks in investment in transmission, and PSE&G is committed to using energy storage as a foundation to solve those problems. And so the Long Island Community Microgrid project brings those other DER resources, the 15 megawatts of solar, as a complement to that energy storage, which is the foundation for that. So it's there is a commitment to deploy this.
Cal Broom is asking, are there any regulatory issues to be addressed to this?
A good question. So the real regulatory challenge here, or barrier, is allowing a utility or community, or together, the two together, to plan for and then interconnect this systems approach to local renewable energy. So we think of a community microgrid as achieving that and having a streamlined interconnection model. And now that the regulatory agencies are really pushing for a lot more distributed energy resources and are understanding all the benefits they provide, the next step is to get away from this one project at a time, one rooftop at a time model, and really get to a scalable solution where we can plan for this amount of capacity and then connect it in a streamlined fashion.
Just so you know, Jack's asking about the presentation. This is being recorded and it will be sent to everybody probably within the next week, so you'll get an email from me about that. This is Sierra. Don Christensen is asking, please comment on how community microgrids would work with community choice aggregation.
Yeah, and that's a really good question. So the community microgrid approach would work with any case where there is community choice aggregation. So there's no dependency on that, but any CCA group that wants to optimize local renewables and other distributed energy resources and get the most out of that from an economic benefit and jobs and everything else, in our opinion, they should take the community microgrid approach to do that. We think that's a good partnership.
Dan Paresh is mentioning that you must know where we can hear an unvarnished explanation of all the challenges that we should anticipate.
Yeah,
we
to
can
me,
bring that up at some other later time and have another presentation talking about a lot of the issues after this is a little further along.
Yeah, and I'll just throw out the biggest issue, which is inertia. Look, this is a new way of thinking about the grid and how to plan for it and to get renewables and distributed energy resources deployed. So it's mindset. That's the biggest challenge. It's inertia. It's getting people to see that this is not only possible, but it's preferable. It's actually a superior way to generate and use electricity in our country. So there are a lot of details under that are challenges, like interconnection, et cetera. But essentially, if we can get everybody to see that deploying this at scale brings benefits to everyone and multiple types of benefits, that'll help us get through these challenges.
All right, and Christina Olson has a question. Can you give a typical example of how community microgrid projects are initiated, particularly who drives it and how they might best approach and work with the utility? Really good question.
Yeah, great question. So in the case of the Clean Coalition, a ton of credit goes to the executive director, Craig Lewis, who pursued relationships with key folks at the utilities, over many, many, many months. Our utilities have a lot of folks who want to figure this out, want to understand how to operate in the new world of distributed energy resources. And so through a little dogged determination, you can find the right people and put a plan together and get the work done. At the same time, my opinion is that cities and communities have a great opportunity here as the customers to really step forward and say, this is what we want. We want this from our utilities, and we want this from our grid that we've spent, billions of dollars on. And so I think both in unison or in parallel, we should be pushing on both sides, or both sides should be pushing for this.
Tom Quebec has a question. Are the batteries used in normal conditions to provide services to the grid? For example, discharge during grid need periods and then possibly empty at the starting time of an unplanned power outage.
Yeah,
We're
the way
just
we've
about out of
approached the
time
use.
here, too, so we're not going to take any more questions than the couple that are still up.
Yeah, so the way that we have approached the battery usage is we reserve, we call this a reserve. So we keep a certain amount of energy in reserve in the batteries so that when an outage occurs, you have that energy there to support the loads. Then the rest of the battery is used for daily operations, whether that's helping with the variability of the solar or storing that solar for peak demand or if there's other generation. So we've got kind of a two-pronged approach for how we use the battery: reserve for outages, and then the rest of the battery use for daily operation.
And Ted Howard is commenting, Clean Coalition has also actively participated in Rule 21 proceeding. To what extent are you planning on following up the Smart Inverter Working Group recommendations for requiring certain ancillary services, for instance, for regulatory, frequent regulation, voltage regulation, reactive power of smart inverters to be required at all the new installations?
Yeah, we're involved in the Smart Inverter Working Group, and we fully support the complete capabilities of smart inverters and use all of those capabilities.
Okay, Ardalan Kamiab, I think I'll pronounce it. What are the three most or more or less, the toughest technical challenges you were faced with creating a microgrid?
I think the technical challenge, and again we're in the the first 5 steps and part of the 6 steps. So we haven't deployed yet, but we're in the prove it's viable steps, and it is viable. The technical challenges are again sort of the way the grid is operated today is, of course, sending electricity from centralized locations to the folks who use it in communities. So everything in the grid is designed to do it that way, and we're talking about adding a bunch of distributed generation. So making the grid go 2 way instead of 1 way, and be dynamic instead of what I'll say is static, although that's the wrong word because loads are changing constantly. And so we have voltage regulation and everything else. But the biggest technical challenge is understanding that the grid is out there, it's an asset, and it's capable of dealing with 2-way generation if you just look at it and analyze it and understand it in that light. And once you do, then if you need to add storage, if you need to add more voltage regulation, great, do it. Support the DER that we need and make the grid modern and make it dynamic and make it secure and resilient. We need to do that.
Robert Perry, this is the last question. What ES technology is being contemplated for utility locations, and are flow patterns being considered?
Yeah, so in Long Island, for example, the large energy storage system at the substation is not decided yet, but flow batteries are certainly a good option there. And the distributed energy storage, the smaller storage at the critical load sites may be lithium. Again, that's not decided, but that seems to be a good option there based on the sizes of that energy storage. So a nice combination of large energy storage at the substation dealing with system opportunities, if you will, and then smaller energy storage at certain sites for backup services and other services.
Okay, we're going to end it here. Thanks to everybody for attending. Greg, it was an outstanding presentation. Thanks for presenting. And we'll check with all of you next time. I'll be sending this out as a recording, so keep your eye open for that. And once again, thanks so much.
Thank you, everyone.